costs something, you can come in and access it. And the YouTube videos, okay, I'm not going to delete them at all. Okay, you use them whenever you want. I'm not bothered at all. If you can use it to do something useful, by all means do it. Okay. And then this line that I'm going to draw, I'm going to change. I'm going to change color. This line that I'm going to draw now in green. Right. This is our neutral axis. And it is offset because you have an axial force. Okay. Now the next one, so this is due to normal stress. Okay, this is straightforward. We have just been through the course on this. Then we are going to combine, right? We are going to combine shearing stress, or we are going to combine shearing stress. Okay. And there are two ways that the shearing stress can be generated. Okay, so the shearing stress, the first shearing stress can be generated by the first one. Okay, the first one is shear force, and we know how the formula look like. And the second one, we did not really do in class. Okay, but there's the other one which is really simple to do. Okay, which is known as due to the torque. Okay, so don't worry about the torque. I will highlight how straightforward it is. Okay, so if we were to write out the equation for the shearing stress, okay, so the shearing stress is equal to Vy over Izz Qz divided by T. Okay, then plus by Vz over Iyy Qy divided by T. Okay, and then there's another one, plus by torsion in the x direction radius divided by J. Okay, so let me gather these terms first and explain what's going on. Okay, so this term over here, as you can see, is induced by the shear force. Okay, this term over here is induced by the torque or torsion. Okay, so including the shear, that's where things get complicated. Okay, I repeat again, including the shear, this is where things get a bit crazy. That's why people rely on software to do structure analysis. Okay, I've checked my analysis with finite element over the years. Okay, on what I'm teaching you, the answer is the same. Okay, now in our program we teach you finite element. Fine. Okay, some of you who are in industry now, okay, and you can answer to yourself quietly on this. How many of you who are in industry now are doing structure analysis have finite element abilities? Okay, I can barely say less than 20% of the companies that you guys work in will have the ability to do finite element analysis. Why? It's too costly. Okay, the software are not cheap. For a commercial license, for any of the software, it can cost you in a company, depending on how big a model you want to build, it can be about $150,000. Okay. is the finite element software all in course or in software? No. Alex, you have to apply what you learned down here for your finite element course, okay? They are going to tell, I've helped the instructor design a course such that they will make you do stuff here to check the answer in finite element also, deliberately, okay? Alex, there's an answer for you. Right. So coming back to here, let's look at the shear force. Okay, let's look at shear force. So if we look at the shear force component, so which is this equation now, I'm going to write it again. Okay, so some of you probably have nightmare looking at this equation. Okay, I had nightmare before. So now if we draw the stress field now, distribution, okay, we're going to sketch a stress field distribution. So we know that this is our shear stress. Okay. And this can be our where am I now? Okay, this can be our y or z distance. Okay, so we know that the center line over here, this is the location of the centroid. So if I were to sketch out the distribution, it will look like this. Okay. At this point over here, this is where you have your tau max. Okay, so this is the shear force component. Then if I were to construct the torsion component, okay, let's see. If I'll let you guys copy first. Then the next one, I'm going to explain about the torsion. Did I make a mistake? Yeah, I did. Thank you, Azam. Then if I were to draw, write up the torsion component, right, where the shear is good Tx R over J. Okay, let me define what are there. So Tx means the torque. Applied about the x-axis, right? R is the radius, maximum radius of the circle, or just the radius of the circle, radius of the shaft. And J is the polar moment, polar second moment of area. Okay, so now I'm going to sketch this out. Okay, how does it look like? So it looks like this now. Let me three. So this is our shear. Okay. So this is only as a function of our radius. So this thing will look like this. The maximum is at the outer radius, the center, the normal stress is equal to 0, and then it goes the other way. Okay, so this again, this position is a centroid. Okay, so now if I were to zoom out, okay, to show you the stress field now, okay. So it happened to be just nice. Okay, I see, can I do this? So you have this sort of profile, right? Then you have another profile. Right. So what is the disturbing thing is this, on the bending and on the bending and on the bending and on the shear due to the what? The shear due to the torsion, you have some similarities. Okay. What is the similarity is the maximum or the zero value is close to the centroid, right? For this and this, there's some similarity is at the centroid, the magnitude is the lowest. But if you look at the shear, right, the maximum is at the centroid. So it's not a problem, but it's a factor. Then with this sort of distribution, right, we are going to apply Mohs circle still to find the principal stresses to select the right material. But now you see the integration, right? You have to integrate the normal stress formula. You have to integrate the shearing stress formula. And then you have to remember 2D or sometimes 3D Mohs circle together with what? With the box, right? Together with the box, your yield. Okay. And then you design everything. Okay. So I'm going to start with the initiation of this topic. Okay. I'm going to initiate the analysis. Again, the analysis is the toughest part. Okay. Okay. So I'm going to pick a problem. Okay. Now, by the way, I've been teaching this course since 2008. Okay, and combining 3D analysis and 3D Mohs circle. Every time students initially have some problems understanding the concept, you have to spend more time on this. Okay, and this is critical. Okay, because this is real engineering work over here now. Okay, so we are going to look at the first example over here, and I'm going to make it in such a way that it's not that difficult. I mean, that's what I like to think, but okay. Okay, so this is our example number 1. Okay, so you can see this structure, right? You can see this structure over here. It is compound loading. Okay, so you have forces acting in different direction. So one thing I want you to take note is you can see the word H and K. Okay, you can see. So this is letter H and K, and these are our elements. Okay, remember our mole circle of elements. These are our elements. So what we're going to do first, okay, we are going to identify